Let's simplify that one topic of dynamic programming, which scares every developer. Let's say you're in an interview, and you're asked to compute the 10th Fibonacci number. You remember the recursive formula. Fib of n equals fib of n minus 1 plus fib of n minus 2. So you write it out confidently. You run it. And then, you wait. And wait. Minutes pass. The interviewer is staring. Your code is still running. Why? Because to compute fib of 10, your function has to compute fib of 9 and fib of 8. But fib of 9 needs fib of 8 and fib of 7. Notice fib of 8 appears twice already. And this explosion continues. Fib of 3 gets calculated several times. Fib of 2 even more number of times. Your computer is drowning in redundant work. This exponential growth highlights the sheer inefficiency of repeatedly calculating the same values. But here's the thing. If you just remember the answer to fib of 3 the first time you calculate it, you never have to calculate it again. You simply look it up. This is the core insight for optimizing such problems. That's dynamic programming. It's not magic. It's not a trick. It's just avoiding repeated work. It's a strategic way to manage computations. And with that one idea, fib of 10 and even fib of 50 solves in milliseconds. That's what we're building today. The intuition to recognize when you're doing repeated work and the tools to stop doing it. Let's see how remembering works in practice. Reintroduce a table, often called a cache or memoization table, to store results, which helps us avoid redundant computations. When we calculate a value like fib of 2, we store its result in our table. This is our first entry into the cache, ensuring we compute it only once. Now, when fib of 2 is needed again, instead of recalculating, we simply look it up in our table. This lookup is the core idea of memoization. We retrieve the stored answer, saving significant computation. This process continues, efficiently avoiding redundant calculations by leveraging our stored results. Notice how the tree visually simplifies, showing a clear reduction in unnecessary work as subproblems are resolved and remembered. By the time we reach fib of 10, our table is complete, and we've solved each subproblem exactly once. This efficiency is crucial for performance. Now, let's compare the naive approach to our memoized solution for a much larger number, fib of 50. On the left, the original inefficient recursion continues to struggle, showing how much time is wasted. On the right, with memoization, the answer is nearly instantaneous. This comparison clearly highlights the immense power of avoiding redundant work. Let's visualize this transformation one more time, seeing the problem and its solution directly. Dynamic programming essentially takes a redundant, bushy recursive tree and efficiently collapses it into a streamlined, linear process. Each subproblem is solved once, and its result is then cached for future use, eliminating wasteful recalculations. The result is the same, but the computational cost is drastically reduced. We've eliminated all redundant work, leading to a much more efficient solution. This is the goal of dynamic programming. At its core, dynamic programming is about remembering what you've already solved. It's a fundamental principle for optimizing recursive problems, turning exponential complexity into polynomial. It's a powerful technique that allows us to solve each subproblem only once, and then reuse that answer whenever it's needed again. This approach dramatically improves efficiency and is a key skill for any professional. So how do we actually apply this idea? There are two approaches, and they're really just two directions of solving the same problem. The first is called memoization, or top-down dynamic programming. You write your recursion like normal fib of n equals fib of n minus 1 plus fib of n minus 2. But before you recurse, you check, have I already solved this? If yes, return the stored answer. If no, calculate it, store it, then return it. You're starting from the big problem and working your way down, but you're caching results as you go. The second approach is tabulation, or bottom-up DP. Instead of recursing, you start from the smallest subproblem, fib of 0, fib of 1, and build up. You fill a table row by row, using previously computed values, until you reach the answer you need. Both approaches avoid redundant work. Both give you the same answer. The difference is direction. Top-down starts big and breaks down. Bottom-up starts small and builds up. And the reason dynamic programming works at all is because of two properties. First, overlapping subproblems. The same smaller problem appears multiple times. Second, optimal substructure. The best solution to a big problem is built from the best solutions to smaller problems. If a problem has both, dynamic programming is the right tool. Now let's see how to apply this framework to real problems. The process is always the same. Define your state, write your recurrence relation, and fill your table. Let's start with the coin change problem. You're given coins of certain denominations, say 1, 2, and 5. And you need to make a total amount, let's say 11, using the minimum number of coins. How do we think about this with DP? First, define the state. Let DP sub I represent the minimum number of coins needed to make amount I. Our goal is DP sub 11. Next, the recurrence relation. To make amount I, we can use any coin that's smaller than or equal to I. If we use a coin of value C, we've reduced the problem to making amount I minus C. So DP sub I equals 1 plus the minimum of DP sub I minus C for all coins C. The base case is DP sub 0 equals 0. You need 0 coins to make 0. Now we fill the table. Start at DP sub 1. We can use a 1 coin. So DP sub 1 equals 1. Move to DP sub 2. We can use a 1 coin or a 2 coin. Using the 2 coin is better. So, DP sub 2 equals 1. Continue this way up to DP sub 11. Each cell depends only on previously filled cells. That's the power of DP. You're building the solution step by step. Let's do one more. Longest increasing subsequence. Given an array like 10, 9, 2, 5, 3, 7, 101, 18. Find the longest subsequence where elements are in increasing order. Define the state. DP sub I is the length of the longest increasing subsequence ending at index I. The recurrence. For each I, look at all previous indices, j, where the value at r sub j is less than the value at r sub I. Then DP sub I equals 1 plus the maximum of DP sub j for all such j. The answer is the maximum value in the entire DP array. These examples show the same pattern. Define state. Write recurrence. Fill table. Once you see the structure, DP problems stop feeling random and start feeling systematic. So where does this actually show up in the real world? Dynamic programming isn't just a coding interview trick. It's a fundamental technique used everywhere. Netflix and Spotify use dynamic programming-based algorithms to match user behavior patterns and recommend content. The edit distance algorithm, which measures how similar two sequences are, is pure dynamic programming. It powers finding similar patterns for personalized recommendations. The edit distance algorithm powers everything from autocorrect to DNA sequence alignment in bioinformatics. This enables fast genetic sequence matching at scale, a critical application for understanding biological data and improving employability in the biotech sector. In logistics and supply chain optimization, the knapsack problem, which asks how you maximize value given limited capacity, is solved with dynamic programming. This helps to optimize resource allocation in complex supply chains, a key skill for improving operational efficiency. Game artificial intelligence uses dynamic programming to evaluate millions of possible moves and choose optimal strategies in real time. This allows AI to make intelligent decisions in complex game environments, a valuable skill in game development and AI research. These aren't toy problems. They're the backbone of systems you use every day. And it all comes back to the same idea we started with. If you're solving the same subproblem over and over, stop. Solve it once, remember the answer, and reuse it. That's dynamic programming. This fundamental principle, first illustrated with simple examples like Fib of 5, is what powers these complex real-world systems. It's not magic. It's not scary. It's just structured problem solving. And now that you understand the intuition, overlapping subproblems, optimal substructure, memoization, tabulation, you have the foundation to recognize dynamic programming problems and solve them confidently. This understanding is key for technical interviews and advanced system design. This is just the beginning. In a full algorithms course, you'll dive deeper into advanced dynamic programming techniques, multidimensional states, and optimization strategies. But the core idea? You've got it.